Welcome to lecture 9 of Mathematical Modeling and Simulation. In this lecture, we are going to understand what are conservation laws and obviously what is their effect or role in mathematical modeling. So far, while discussing the process of mathematical model, I told you that there are 4 ways roughly to do that. The first one is dimensional analysis, which we have already discussed. Scaling also has been discussed. In this lecture, we'll be focusing on conservation laws, and in the next lecture, we'll be focusing on linearization. So without a delay, let's begin with conservation laws. So firstly, we'll understand what is a conservation law, and then specifically we will look at energy conservation and mass conservation, and finally we'll derive continuity equation, and you will get to know what exactly is continuity equation. Okay, so why to study conservation laws for modeling? So before even telling you what is a conservation law, let's first try to answer this question, that why we need conservation laws for mathematical modeling. So if you recall the detailed process or principles of mathematical modeling, the very first step was to identify some real world phenomena for which we want to write or develop a mathematical model for, or we want to understand it through mathematical modeling. Suppose you have some problem in your mind, you're already working on some real world process, and now you want to build or develop a mathematical model for the same. So the question arises in our mind, what's next? Okay, you have decided to model, but what should be done next? Where should we start from? We should have something in our hand so that we can write some mathematical expression or then start our calculations or analysis based on that. We should have some mathematical equation in front of us. So that's what we start thinking. We think of writing a mathematical expression for the dynamics of the system depending upon whatever be the underlying problem. So that's when conservation laws comes in our mind. So conservation law is basically a way to develop or to begin the study of certain systems through the process of mathematical modeling. It's not true that every mathematical model is require the study or the application of conservation laws, but many of them, many of the systems in fluid mechanics or traffic flow, and we'll have various examples throughout the course, which do require the usage or the application of conservation laws. So now we answer, what is a conservation law? A particular measurable property of an isolated physical system does not change as the system evolves over time. So there is something called conserved quantity. So a system is having many quantities. It's having energy, it's having mass, it is having momentum, it is having temperature, it is having current. So whatever be your underlying system is, it's having certain measurable things. So there are certain measurable properties which are not changing with respect to time. They remain conserved or they remain constant in one or other sense. But the important point here is that the system should be isolated physical system. Isolated means, in other words, it's closed system, it's not an open system, because in open system, when you allow the exchange with the boundaries or with the external surroundings, then there is no point of talking about conservation. So conservation laws are applied only to the closed system, on the finite closed systems. So they do not exchange anything with the surroundings. So in such systems, you are definitely going to find some quantity which is going to remain same over time, or it's going to remain conserved with respect to time. So that quantities are called conserved quantities. And according to classical physics, we have these conservation laws: conservation of mass, energy, charge, linear momentum, and angular momentum. Why I have written classical physics here? Because in the modern physics or the particle physics, you can say we do have conservation of some particles like baryons and many other molecular level or atomic level particles. Let's not talk about that here, because right now the kind of systems we are going to study are well defined within the range of classical physics. So these are the conservation laws we are going to have. We are not going to study or look at them, all of them, because most of them you have, in fact, I think all of them you have studied in your earlier classes, but the kind of examples you did there was different from the kind of examples we'll be doing further in this course. So let's continue. In general, now I'll tell you how to write the general equation of a conservation law. So it's like an alternate way of writing conservation law, or you can say a mathematical way of writing conservation principle. So a conservation principle states that the rate at which the quantity, so that's the general notation, qt, changes has to be accounted by how much of the substance goes into the system and how much of it goes out of the system. So it makes sense. So suppose you have a closed system, then you want to see the rate of change dq by dt. So it's q in minus q out. So you have a closed system here. This is in, this is out. So the change is happening inside is definitely difference of the mass flux going in, which is called influx, and the mass flux going out, which is known as outflux. So flux is a general word for flow rate. Something is changing, something is flowing. Fluid is moving, gas is moving, air is passing, some liquid is flowing through a pipe. So whatever flow is happening in a particular section of the system, so in that particular section, the quantity which is going to change. So if you want to know how the system quantity, whatever is the quantity, mass or volume you are measuring, how that is changing in this finite closed system, so that is actually depending upon how much is going in and how much is going out, because that's the basic meaning of conservation, that nothing is lost or nothing just disappears like that. Whatever goes in, a part of it stays inside and rest of that out comes outside, because the quantity has to be conserved. There is nothing like something which is lost or disappear on the way. So that's the fundamental intuitive way of applying the conservation laws, and exactly the same thing we'll do in one of the derivation. So firstly, I have taken law of conservation of energy, although its applications are vast, but here the aim of this lecture is to make you understand how to fundamentally apply the conservation principles to deduce the equations. So to understand that, for the beginning, I have taken a very simple example of a pendulum, but before that I can state like energy conservation in this way. This is the definition we all know: energy is neither created nor destroyed, just gets transformed from one form to another. In other words, total energy is constant. So let's begin with the example of swinging pendulum. So suppose it's making an angle theta here, L be the length of pendulum, M be the mass of it, and H be height above the ground. Then the energy associated is gravitational potential energy, because when you displace the pendulum from its equilibrium position to certain height, you give it an angular displacement and raise it at a certain height, then because of the gravity it acquires a gravitational potential energy. In general, we also call it just potential energy. So even if you call it potential energy, that's fine, but the general name is gravitational potential energy, and we all know that it's given by mgh, where m is the mass of the object, g be the acceleration due to gravity, and h be the height above the ground level. So if you want to simplify this expression further, we can have this in terms of L. So in equilibrium position, this total length is going to be L. The small one is h. So h is L minus AB, where A is this point and B is this. AB is L cos theta. It's very easy to see. So we get an expression for h. So if you substitute this h in the formula for potential energy, will get mg L into 1 minus cos theta. And the other energy we are going to look at is kinetic energy, which is coming due to motion of the pendulum, due to oscillation. It's half mv square, which can be written as half m dx by dt square. because when you set the pendulum in motion, it starts oscillating, so it will generate an angular velocity associated with it. So basically this v is the angular velocity. It's further given by dx by dt. Actually it should be d theta by dt, because there is no other kind of displacement we are talking about. We are talking about angular displacement here. So anyway, that does not matter, because right now we are not going to use this expression any further. My idea was to introduce you, whenever you start applying conservation principle, energy conservation principle, then firstly you have to figure out what are the various kinds of energies are associated with the system. So we have two energies, potential energy and the kinetic energy with us. Now using the law of conservation of energy, we get the sum of both the energies is E, which is constant. So this is basically, you can say, is governing equation for a simple pendulum. So that's it. You wanted to understand how the pendulum is moving, or how its velocity is going to be connected with its length or mass or the angular displacement. So whatever you want to analyze, you need to have a mathematical equation for that. So using energy balance principle or energy conservation, we have got an equation. Right now, I'm not going to explain you further analysis or detailed calculation of this equation, because as I just told you, here we are just understanding how to use or apply conservation principles to reach the equations. So we got an equation. So that's about conservation of energy. So you can apply this energy conservation principle on any of the example, and many other examples are there. But right now we are going to move towards next law, law of conservation of mass. Again, if you want to know the definitions, you clearly know that mass can neither be created nor be destroyed. There's nothing like which suddenly disappears. It just shifts from one place to another because of the continuous evolution of a particular system. So to understand this, I have taken the example of a section of a pipe in which certain fluid is flowing. You can have the example of water, and because I want to apply it over a small conserved system, small closed system, so I have defined two positions, x equals to x1 and x equals to x2. So these are the boundaries of the system. So these are just representing the molecules, just for the pictorial representation, but we know that the fluid is continuous, the liquid or whatever it is. Omega is just a notation, doesn't matter right now. This is the inflow at the left boundary, x equals to x1, and this side it's going outflow. So this is just to depict the direction of the flow. So you consider the flow of water or liquid or any fluid through a pipe inside a section of length x1, x2, and then over this section I'll be applying the law of conservation of mass. So we get the rate of change of fluid inside this section x1, x2 is equal to the difference in outflow and inflow at x equals to x2 and x equals to x1 respectively. That's the general way of applying conservation law, which I just told you a few slides back. Now we'll write the corresponding mathematical formula for the same. So basically you can understand it like whether you call it law of conservation of mass or you call it law of conservation of volume, that does not matter, because we know that how mass and volume are connected. Density is mass per unit volume. So density, if you assume to be a constant, so you know if mass is conserved, so volume is also conserved, because whenever we are talking about liquids or fluids, we usually talk about volume, how much volume of a fluid is there inside a particular area or a particular section. So it does not matter whether you call it a volume conservation. And the next thing is, here we have taken the example of one-dimensional flow. I have not assumed or I have not considered any flow of the fluid in the vertical, in the y direction or in the z direction. Although we know that in general, whatsoever kind of pipe flow you consider, the velocity is definitely going to have three components, x, y, z direction. But just for simplicity, because we want to begin with, we want to understand the one-dimensional version of this model. So let's write what is the rate of change of fluid inside this. So rate of change of fluid means d by dt of something. So d by dt of the mass, and mass is going to be given by density into volume, and volume is here basically the dimension of length is there because it's one dimensional problem. So it's d by dt integral x1 to x2 rho xt into dx is qx1t minus qx2t, where rho xt is the density of fluid and qxt is the flux, which is the rate of flow of fluid per unit time. You need not write per unit time because rate means okay per unit time. So rho clearly, density is clearly a function of space and time. So in space we have taken only one dimension, which is x. If the problem would have been in two dimensions, so it would have been x, y, t, and otherwise in three dimension it's x, y, z and t. So usually our variables or the fundamental variables are always functions of space and time, and our flux is also a function of space and time. So this is the difference between, so this is the influx, you can see this is the influx, this is the outflux. So this is something which is happening inside that section. So this is density into volume. So this is representing mass in a small section dx. So dx be basically, you can say, a small kind of strip over here. But if you want to find it over the complete interval x1, x2, so you need to integrate it from x1 to x2. And now what further we are going to do with the right hand side. So the right hand side can also be written like derivative of q with respect to x and then integral, which further gives. So I'm coming to what further is there, but let's first understand what is how this is written. So we know that a function can be written as the integral of its derivative, because integral is basically the antiderivative. So it will just kind of cancel out and you'll get the function back into the picture. So this is the value of q at x1, this is the value of q at x2. So since on left hand side the integral is from x1 to x2, the lower limit is x1 and the upper limit is x2. So on right hand side also I have tried to keep it same, the lower limit x1 and upper limit is x2, because when you will integrate of the derivative, then you will get the function back, and therefore a negative sign has been taken outside, because only this much will give you q x2 t minus q x1 t, because the integration is happening with respect to x variable, so t remains just t. It's a partial derivatives involved over there. And since I want its q x1 t minus q x2 t, so that's why negative sign has been taken outside. So that gives you this equation. And now what I'll do, I'll shift this d by dt inside, because I want to now compare both the sides, so the integration should be taken common. So d by dt when will be shifted inside will become the partial derivative. So that's just coming from the basic rules of calculus, because your underlying variable is just not a function of one variable, it's a function of two variables. So you'll get it del rho by del t, and you shift the right hand side to left hand side, you get this 0, which further gives you del rho by del t plus del q by del x is equal to 0. This is called the integral form, and this one is called the differential form of conservation of mass, or famously known as continuity equation. So very famous equation in fluid dynamics. You need to remember this equation because we'll be using it further also, but right now this is just about the derivation of it. So you see how we are just using the basic principle of law of conservation of mass, and nothing else has been used except few properties of the calculus, and we have got a very nice equation with us, which is connecting the three variables, or you can say two variables, rho and q, and both of them are functions of x and t, space and time. Rho is the density, q is the flux. So that's the differential form of conservation law, and it is really having many assumptions underlying, because to be the function should be differentiable, only then you can write its derivatives. The function should be smooth enough. So all those underlying assumptions for these functions are there, although I have not mentioned them, but they definitely come into picture whenever you are talking about the integrals and the derivatives. So the functions, all functions should be smooth and the continuous and the differentiable. So that's the law of conservation of mass derived. And right now we are not going to do any other conservation principles, because you have just got the idea how to use any conservation principle or any physical system to get a governing equation of the same. And rest depends upon whatever particular examples we'll be doing in our course. We will apply whichever conservation principle is supposed to apply over there. In the next lecture, we are going to look at, last but not the least, one of the methods of process of mathematical modeling, which is linearization.